In the last lecture, we started talking about linear classifiers, and we're going to continue today talking about linear classifiers. And we had talked about, maybe for the last two lectures, how we could build classifier with what's called a discriminant function. So we could say that we could generally build a classifier with discriminant functions and we had called them delta C for each of my classes. C goes whatever. You can kind of generically call them classes 1 to, let's say, K. And so that the idea is that delta C of some X, this thing is going to be large if given X signifies that the associated Y is likely to be in class C. Associated Y is likely to be in class little c. So the idea is that we can calculate the discriminant function, and we can then predict our class, which is y hat now, which is now just a class. We can predict y hat as what we do is we calculate dc or delta c over all of our classes, and we let y hat be the class that has the largest discriminant function. And we said a Bayes classifier basically you can interpret it as letting my discriminant function be the probability, or in reality, an approximation of the probability that y is in class C given I observe my little x here. And so that was a general setup. And we had this definition, which was that a classifier is so-called linear if some, let's say, increasing but kind of generically monotonic function of the discriminant functions is linear. And we could even say that in this case, the decision boundaries between classes are lines, or are linear. So the idea with a linear classifier is that the decision boundaries are going to be kind of piecewise linear. And so as long as either the discriminant functions, or we can kind of monotonically transform them into a form where they're linear, that's going to give us a linear classifier. And we looked at K and N. K and N is not going to be a linear classifier. And you can see that just from, if you go back to our lab with K and N, you can see all these wonky decision boundaries, which are definitely not linear. But we had talked about our first technique, which is called linear discriminant analysis. And this is a linear classifier. And linear classifiers basically are going to play the same role as kind of linear regression, which is that they're going to be the building blocks, the kind of simplest building blocks of techniques. So we have linear regression, and you can use that to build more complicated techniques. You could do transformations to your parameters, and we'll talk about even more complicated techniques as the course goes on. And in the same way, that linear regression was the first regression technique to be discovered, as it were. The linear classifiers were the first classifiers to be created also. And so they play historically kind of a similar role, and in a similar way, we were going to be able to kind of modify them and recombine them into more complicated things, or at least understand the more complicated things in light of how they behave similarly or different to kind of the simpler linear classifiers. In linear discriminant analysis, the most simple way we can think about it is that our discriminant function, which is going to be probability that y is c given our x, so it's going to be a Bayes classifier. We said that by Bayes' rule, we can switch things around and calculate this as the probability we observe the x given I'm in class C times the probability I'm in class C. And I say proportional to, but the proportionality constant doesn't matter. It doesn't depend on class, so we don't really care. In linear discriminant analysis, the kind of one way of viewing it, and maybe next time we'll talk a little bit about another way of viewing it, but one way of viewing it is that it's going to make some assumption here. And this assumption is going to be that the class conditional probability, if I know my x is associated with a y from class C, which is how we read that first probability. Probability is a little bit of an abuse here because it's going to be continuous, but I'm going to abuse notation. We're going to assume that it comes from a normal distribution with a mean that depends on the class and a variance that doesn't depend on the class. It's the same for all the classes. And then the probability we're in class C, or so-called prior probability, is just going to be some number. We'll call it pi c. And what we had showed with algebra is that we can write this discriminant function actually is linear in x. It's going to be x times mu c over sigma squared, and this is just a kind of simple transformation, minus mu c squared over 2 sigma squared plus log pi c. And we had said that therefore this thing is linear because you could view this as some beta and you can view this as some intercept beta naught. Of course, we'll then the class, so we'll add a little class there. And the whole kind of analysis of linear discriminant analysis is that we have unknown parameters mu c for each class, pi c for each class, and sigma squared. And we estimate these using the training data. And that will give us estimates. So we'll get mu c, which is the mean of the x's, xn's, the training data points in class C, right? So our training data is going to be sum of class 1, sum of class 2, sum of class 3, sum of class 4, etc., etc. So if we take the means of the x's in class 1, that's mu1 hat, means of the x's in class 2, mu2 hat, etc. Pi hat for each class is just the percent of my training xn's in class C. And sigma squared hat is so-called pooled variance which is a fancy way of saying it's a weighted, what do? We calculate variance separately. Let's even say we use the sample variance. We calculate the sample variance separately for each class, and then take weighted average of these things. So this, the familiar, sample variance, we do it, we calculate it for the x's in each class, just like the same way we calculate the mu hats in each class. And then but because we assume they all have the same variance, we can actually pool these together. And so we just average them together, those estimates. And we do a so-called weighted average because it's possible we have a different number of training points in each of the classes, so we weight kind of inversely with the number of training points we have. But it's kind of a little detail. It's not super important. And once we have those estimates, we plug them back in to this equation here, and that gives us our final discriminant functions. So we had done this for, in this case, we had our x here was just some number. And we can expand this to when x is a whole feature vector. So instead of having just one feature, one x and the corresponding y, we have a vector of features. We have multiple features we've measured. And we do this using the so-called multivariate normal distribution. And so the univariate normal has our kind of familiar bell-shaped form, where we have some mean mu that tells us where the center of this thing is, and then we have our variance sigma squared that tells us how wide this thing is. The multivariate case is just a generalization of this. So maybe I have if I want you could have a 2-dimensional normal, 3-dimensional normal, 4-dimensional normal, etc. It's a straight up generalization. In the 2-dimensional case, I would have x, y, and then I'd have some z plane. So maybe I have an x, y, and z plane. And we're basically going to get a 3-dimensional bell-shaped looking thing. It's a bit hard to draw in 3 dimensions, but something like that. And we will have a center point, which is mu, and then how wide this bell is. This bell is kind of these concentric ellipses. The wideness of this bell is controlled by a parameter capital sigma, which is called the covariance matrix. So here mu is some p-dimensional vector, and sigma is a p by p matrix, which controls how that bell is kind of shaped, elongated in one direction or another, or maybe it's symmetric. And so mu is just the coordinate means, and sigma is the covariance matrix, where one way you can think of this is that the ijth entry of sigma is going to be exactly the covariance between the I and jth components of an x if it were distributed in this way, a multivariate x. And if we look at the PDFs for these, in the univariate case, our PDF fx has our favorite form, 1/√2 pi sigma squared, e to the negative 1/2 sigma squared x minus nu quantity squared. And in the multivariate case, we now have an x that is p-dimensional. And it's kind of similar. Instead of, you could write this first part here as like 2 pi to the negative half sigma squared to the negative half, right? And so in the multivariate case, it is actually going to be 2 pi to the negative, instead of half, it's p over 2. We have p components. And then instead of sigma squared to the negative half, it is actually the determinant of this matrix, this covariance matrix, sigma, to the negative 1/2. And then we get our exponential. And instead of what we have in the univariate case, you could, it's not clear why you would want to, but you could write this as negative 1/2. And you could write it as x minus mu times sigma squared to the negative 1 times x minus mu, right? That would be an equivalent way of writing that in the one-dimensional case. And that most straightforwardly generalizes to the multivariate case, where the argument or exponent is negative 1/2, and we get x minus mu transpose sigma inverse x minus mu. And so you can see the kind of symmetry there, where sigma, capital sigma, the covariance matrix, plays the role of the variance, the univariate variance, sigma squared. And we have to add in some transposes to make sure everything works out. You can think about the dimension of this argument, right? This thing better be just a real number. So this thing is, if x and mu are 1 by p, this would be p by, x and mu are, let's get this correct, are p by 1, then this thing should be 1 by p, that's right. Sigma, and hence sigma inverse, is p by p, and we're going to assume, for the sake of argument, that x and mu are p by 1. And so this whole thing here is just 1 by 1, that is, it's just a number, and so you multiply by negative half, you exponentiate it, and you get out, at the end of the day, just a number, which is all that a density function gives you. But from there, basically all we do for a multivariate linear discriminant analysis is we're replacing this univariate normal distribution with a multivariate normal distribution. And so if we go back up here, this is the assumption that we made for the univariate case, and we can get a kind of similar thing going for the multivariate case, where the discriminant function is, so again, it's my class conditional probability. Probability I see my x, given that x is associated with a y of class C, times the probability my y is in class C. And this quote probability really is a density, but one way you can interpret that is now for our multivariate case, we're going to have a mu c, so a whole vector mu c. Again, mu c is what did I say, p by 1, and sigma is p by p. But I have a different mu for each class, same covariance matrix now, and this thing is still just some class probability pi c. So cool, that's nice. So we can actually work this out now, because we can plug in what our density function is, and we can derive our discriminant function. So for class C, this is 2 pi to the negative p over 2, determinant of sigma to the negative 1/2, exponential, negative 1/2, x minus, now it's, for class C, it's mu c, and then we multiply by pi c. So you could stop there. That is our discriminant function. And if you actually need to calculate LDA, we'll talk about it, but you'd estimate the mu, you'd estimate the covariance matrix, you'd estimate pi, you plug in your estimates, and then given an x, after you've gotten those estimates from the training data, you'd produce delta C for the x, and you'd maximize it. You'd find the class with the highest delta C. That would be your prediction. Of course, in the univariate case, in the one-dimensional case, this thing was a linear classifier. And so the question is that going to hold in the multivariate case? Well, we can see. So let's see if that's going to hold. If we look at, I'm going to write it like this. We're going to log transform. I don't have to come up with a different name for the discriminant function each time. I'm going to reassign. I'm going to rewrite my discriminant function to be log of this. And frankly, I'm going to ignore everything that doesn't depend on the class, right? Because it's not going to affect, it's going to show up on all the discriminant functions, so it's not going to affect which one's the largest. As long as it's monetized, as long as I don't flip a sign, right? That would be bad. But as long as I'm just getting rid of like positive constants, like 2 pi to negative pi over p over 2, it doesn't depend on the class. This determinant of sigma, negative 1/2, that's positive, doesn't depend on the class, I can ignore it. So if I take a log of this, right, I'm just going to pull down my exponent. I'm going to ignore these things. And I get x minus mu transpose sigma inverse x minus mu c, and I get plus log of pi c. And what do I want to do? Well, I'm just going to basically distribute this, square this whole thing out. This might be a bit messy. We'll see. Yeah. So let's kind of square this whole thing out. So, yeah, there's going to be a lot of cross product terms, but let's just do it one step at a time. So we have negative 1/2 there. I can distribute my sigma inverse through, and I can also distribute my transpose through. So this is certainly going to be x transpose sigma inverse minus mu c transpose sigma inverse. And so that we can distribute through. I have my x minus mu c, and I got a log of pi c, and I'll keep going along. This is not too bad. You know, the rules of distributing these things through, because it's all just multiplications, is actually not so bad. And then I can do a cross product, a FOIL thing here, distribute my x minus mu c through. What am I going to get? First is x transpose sigma inverse x. Right? Okay. And inner, I guess it's not going to be inner, but there's going to be multiple. Let's do the last thing, which is x transpose sigma inverse mu c. And actually, I need a minus sign there. And then my cross product terms are minus x transpose sigma inverse mu c. What's the other cross product term? Minus mu c transpose sigma inverse x. And I guess this term would be a positive, right? Because I would have a negative and a negative. Let's not mess that up. Doing algebra, especially linear algebra on the fly, is always dangerous. And of course, I get my log of pi c. Okay. Now, what don't I actually care about? So I guess I guess my 1/2 wraps around all of that, right? Okay. So I think that works. X transpose sigma inverse x. X transpose sigma inverse mu c. Oh, I'm doing this all out of order, aren't I? So that's a minus mu c. I think I've written things multiple times. Let's try this more. Minus mu c transpose sigma inverse x. So that's that. And I get a minus. There we go. There's our plus. Mu c transpose sigma inverse mu c. Okay. Okay, I think that's correct now. Now notice anything that doesn't depend on the class, we can ignore, because it would be the same for all discriminant functions. So that we don't need to care about. And there anything else that we don't care about? I think that's it, right? Yep, that seems right. And notice that this thing and this thing are the same. If you work out the dimensions, they're just numbers. And first of all, they're transpositions of each other. So you could apply transpose to one, and you get the other. And because they're numbers, the transpose of a number is just itself. So those are actually the same thing. And so at -1/2, I get 2 of these, and a -1/2, both those are minus, so I actually just end up with x transpose sigma inverse mu c. I get a -1/2 mu c transpose sigma inverse mu c, and I get plus a log pi c. Okay. Enough torturing for now. So that's my discriminant function. We call this my discriminant function. And just put a box around it here. Notice again that I could, if I let this thing be beta and all of this be beta naught, then this would be x transpose beta plus beta naught. And that is linear. It's written as just an inner product between some beta and x, and you add on some intercept. So this is actually, again, a linear classifier. So even in the multivariate case, or let's say multivariable case, p bigger than 1, this is a linear classifier. Which is settling because it was named linear discriminant analysis, so we hope that is a linear classifier. And the idea with this linear classifier here is that if this is like, if I have like p is 2, and this is my x1 and this is my x2, and maybe I have some red class points here, so these are my training points, and I have some blue class points over here. You know, if you go back to the notes on the one-dimensional case, I kind of fit these normal distributions to it. In this case, you can think about exactly fitting a multivariate normal distribution to it. So I'm basically going to fit a mean here. Let's say mu1 hat, and I guess this would be class 2. This would be mu2 hat. And I'll fit a common covariance matrix, which is going to tell me, so we're kind of looking down on top of these, on top of the normal distributions on the multivariate normal, and these circles are supposed to be the same size. Let's say they fit some kind of similarly sized covariance matrix, so they may have these distributions of different means, but the kind of way they're distributed around those means is similar. And then, you know, I'll get my kind of contours. So these are my contour lines of, you can think of that, of my multivariate normals. And the decision boundary is going to be something like that, separating my two groups. So here I predict my circle, my blue circles. Here I predict my red x's. Right, on this side of the line, I predict the red x's. Other side of the line, I predict the blue circles. And that gives me my classifier, and the decision boundary, at least for 2 classes, is just going to be a line. In multiple classes, it's just going to be kind of piecewise lines. So that's kind of how you can think about it. We estimate. So the question is, how do I estimate my mu hats? And I need a covariance matrix, sigma hat. And you can imagine that mu c hat is just the mean vector of x's, my training x's in class C, and sigma hat is a matrix, and the entry is just going to be basically and I'll leave it a bit vague, but it's the pooled covariance between the ith component of the xn's and the jth component of the xn's. I'll leave that a bit vague about what pooled covariance actually means, but pretty much you can imagine separating it out for each class. You estimate the variances and the covariances, so and then you kind of do a pooled or a weighted average of those, and you get what's called a pooled covariance matrix. But frankly, for our purposes, it's not too important to worry about it. But you get a linear classifier. And what I should point out here is that just like in regression, I can, even if I only have one x I actually measured, I can always create more x's, more dimensions with transformations, right? So in my original kind of linear regression, maybe I had an x, but I could fit a regression of x and x squared and x cubed. I could add transformations in my original variable to enhance the space, basically growing p. So this is basically would grow p, number of covariates. And you could do the same exact thing for linear discriminant analysis. I mean, you can do the same thing for k and n too. You can do that for any of these. The x matrix, you don't need to think about it as, this is why we refer to it as kind of the design matrix. You don't refer to it as the measured variables matrix, because it's not necessarily the measured variable. It's you can have transformations of your variables. And so you can always, let my x matrix or my training data matrix, be x as the first column, x squared, that's the second column, log of x as the third column. So you can add on things. So you can always make your space richer and move from the univariate discriminant analysis to the multivariate. It's still going to be a linear classifier in this new expanded space of variables, but in the original space of x's, it will be kind of nonlinear. So there's a little bit of interplay there, but just that's an FYI. And we'll see that when we look at it in the lab. Just like regression, you can add on various transformations. You can do this for linear discriminant analysis, and you could do this for k and n. You could do this for lots of things. Okay, so the next kind of add-on here is we want to talk about what's called quadratic discriminant analysis. And this is not a linear classifier, and the name signifies that because it is quadratic, but it is highly related to linear discriminant analysis, and so it's worth talking about here. Let's talk about it. So if we go back to our simple two-variable case, LDA kind of assumes equal variances, and QDA says, let's relax this, different groups or classes, let's say classes can have different variances. So the picture in mind here for the one-dimensional case, if I have some red x's in my training data over here, and I have some blue circles, and my blue circles maybe are really tightly packed compared to my red x's, it might not be reasonable to be assuming here that my variances between these groups are equal. And so in LDA, I would basically fit a normal distribution to each of these, but they would have the same variance. QDA relaxes that, therefore it's a more flexible method, but it's going to allow me to fit normals to these with different variances. So I'll have, sigma x squared for my x's, and I'll have a sigma circle squared for my circles. And so it is a more relaxed assumption, relaxed model. It's more flexible. And so for LDA, we had to estimate otherwise it's pretty much the same, right? Is what I want to say. LDA, you had to estimate the means for each group, you had to estimate the prior probabilities for each group, and you had to estimate a common variance or covariance. Let's just call it sigma for the most general case. And QDA, you similarly have to again estimate my means, have to estimate my prior probabilities, but now you're going to have potentially either a different variance or covariance matrix for each group. But otherwise, it's basically the same deal. Let's say discriminant function for QDA, right? So the discriminant functions are going to be very similar in so much as it makes certain normality assumptions, right? You can still view it as this Bayes classifier where it's using Bayes' rule to approximate the probability that, and so it looks at the class conditional probability I observe my x given this in this class I'm supposing, times the probability, kind of prior probability that we observe something in that class. And now what LDA did was say this was normal mu, let's say sigma, and this was pi, that depended on the class. QDA is just going to add a c there. It's going to say, okay, that can also depend on the class. And unfortunately, as it turns out, fortunately or unfortunately, this is no longer a linear classifier, which is okay. So what happens is that basically what this means is that the fact that we had equal covariances or equal variances among the groups was leading to the linearity of the classifier. That's what made that linear, at least in that case. And when we relax that assumption, we lose that linearity assumption. Now, I've done the derivation for LDA both in the univariate case and I've done it in the multivariate case. So I'm not going to recapitulate that whole discussion and whole derivation. So let me just say, in the case where I have just one covariate, our discriminant function, delta c for our class, is for QDA is now negative log sigma c minus x minus mu c squared over 2 sigma c squared plus log pi c. So that's one way to write the discriminant function. Of course, any monotonic transformation of that is equally valid, but you can compare this to the one-dimensional case. Notice that in the one-dimensional case, we said, that's linear, therefore we're all good. In the two-dimensional case, we have a quadratic. And we can't get rid of this quadratic in this case. There's no way to do that. No way to get rid of it. It is a quadratic that we're just stuck with. And so hence the name quadratic discriminant analysis, or QDA. And so it turns out that the discriminant functions for QDA depend quadratically on x. Therefore, it's going to quadratic in x. In a linear classifier, you can call it a quadratic classifier. No one really does, but you could. And the reason why you can't get rid of this is because we have this sigma c squared in the bottom. Before that didn't depend on the class, and so we could just ignore it. But now it does, and so we're not going to be able to get rid of any terms if we were to square at that quadratic, and so we're stuck with it. But this what it is. It's a nice classifier. You could do the same derivation p bigger than 1. And now, instead of having just a sigma squared for the class, we have a whole covariance matrix. And the discriminant function in that case is negative log determinant of the class covariance matrix, sigma c, minus 1/2 x minus mu c transpose sigma inverse x minus mu c. So this looks kind of familiar. And then we have our prior class probability plus the log of pi c. So yeah, so that's the case here. It's, you know, it's related to LDA. It's we'll look at it in the lab. It's in many ways not that interesting, but it's worth mentioning because you'll see this crop up occasionally, and in some cases it gives you a little more flexibility than you would get with LDA. So we can do a quick little comparison of them. Let's say LDA versus QDA. So we can look at, say, the number of parameters and if we look at the number of parameters for these two, for LDA, you can count up. I'm not going to make you count up the parameters. For LDA, you will find that if I have k classes, I'm going to have k minus 1 times p plus 1 parameters I have to estimate. So if I have 2 classes, that is just, and if I have 2 classes and I have 1 covariate, that should give me 2 classes, 1 covariate, 3 things to estimate. You have to think about why that's true. It's a little less trivial than you think because the probabilities are related, have to sum to 1. So there's a constraint with the probabilities. So you only actually have to estimate 1 fewer probability than you think. Basically, you have to estimate what do you have to estimate? You have to estimate the means and one of the prior probabilities and the variance, let's say. And for QDA, you have to estimate, and this is even more complicated. Yeah, so the counting arguments for these are a little complicated because even the LDA one seems fishy. So it turns out you don't actually need to estimate all of the parameters. You only have to estimate like you don't actually have to estimate all of the discriminant functions. You only have to estimate, be able to estimate kind of ratios of them because then you can tell which is bigger. Point being, if you don't believe me here, we can talk about it. But if you, it's a little less trivial accounting problem than you think. But basically, the punchline here is that if I want to use LDA, I basically have k times p parameters that I'm going to end up estimating, and if I use QDA, I'm going to basically have k times p squared. And so what this says is this is much more flexible. So basically, that's, you know, the number of parameters is kind of the dimension of this functional space in some ways, right? And so we have a higher kind of dimension of possibilities for QDA. So we have a richer set of functions that we can estimate. And so it's more flexible, and that comes with some advantages and some drawbacks here. So the last thing that we should talk about in class today, in this last couple of minutes, is we've now looked at linear classifiers, right? So we've looked at, in particular, we looked at LDA as our first linear classifier. So LDA, let's say very simply, is a linear classifier. And the discriminant function for LDA is some intercept for my class plus some slope for my class transpose my covariate feature vector, right? And that's the discriminant function. If I give you the discriminant functions, I give you the I give you the classifier, because it's kind of a one-to-one relationship there. And what I do is LDA is basically a procedure for estimating the beta knots for my classes and the betas for my classes using training data and an assumption of normality. So that's one way you can do it. Even if you don't, it makes some assumption, even if you don't care that it's particular about normality, it makes some assumption about my data, and it does something to actually get estimates. Those estimates, these betas, are somehow related to the mu hats, the pi hats, the sigma hats, right? In some complicated way, for example, when we looked at, back up to our case, this beta hat would be sigma hat inverse mu hat c, right? And so it's complicated, but you can, in some broad sense, you can just view LDA as a linear classifier. So it's going to have a discriminant function that have an intercept plus some slope times my feature vector x. And then LDA is a certain way, right? So that general up to this point here, that's just generally a linear classifier. So maybe we could just say this is just all linear classifiers. And they have that form. LDA is a specific one, and it specifically works by making some assumptions about our data, about normality, about equality of variances, things like that. And it uses those assumptions to get us estimates. And those assumptions, just like linear regression, will reduce the space of, down to estimating a beta hat and a beta, an intercept and a slope, for example. LDA makes some assumptions to get our beta hats. And the question is, why did we have to go through all of that, right? This looks like just regression. So why couldn't we figure out these beta hats with just regression? So let's just talk about that for the last couple of minutes here. Why not use regression to find beta hats, right? It seems like this is just basically linear like regression, except now my y is categorical or something. And so why do I have to go through this whole thing of normality and blah, 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 and deriving this whole thing? What you could imagine doing is, let's consider like a binary classification problem. And I'm going to try and draw two of the same picture, where, okay, so I have my red x's over here, and in one situation, I'm going to code my x's as zeros, and I'm going to code my blue circles as ones, and maybe my blue circles live up here, right? And the other situation, I'm going to do the opposite encoding, where I'm going to encode my red x's as ones and my blue circles as zeros. So something like that. And what if I just fit a regression line? So, oops, that's probably not going to be it, but let's say regression line. So I could fit a regression line in that case, and I could fit a similar kind of regression line in this case. And what if I call the one where I'm predicting my circles the discriminant function of my circle class and the one where I'm predicting the x's are 1s, I'm going to call that the discriminant function for my x class, right? And it will be sum intercept plus, plus slope times x, and similar here. That is a valid approach. So here our approach is to use some kind of binary encoding of variables. Let's not say variables, of covariates. Nope, not even covariates, of the y's. Binary encoding of these y's, either a 0 or 1. So we do it one way and then we do it another way. This is the 2-class problem, but you can imagine doing it for a multi-class problem too. This could be extended pretty easily. And to do this binary encoding y's and fit regression line, because basically I've taken it from categorical to now I have actually quantitative data, and so at 0 and 1, I can fit that. I can fit a regression line to that. And we fit a regression line to this. And use as discriminant functions. And so basically what I'll get here is I'll get my discriminant function is some beta naught c hat plus beta c hat times x, something like that. Even if you do multivariable regression, doesn't really matter. And where I got in these, so it's basically the same linear classifier setup, but these are obtained from just our simple least square regression, which we talked about way back in whatever lecture 2 or whatever. And so the answer is you can do this. This is a thing you can do. It's absolutely a thing you can do. And it's not the worst idea in the world either. Because any procedure to develop a discriminant function will give me a valid classifier. It might be good, it might be bad. The procedure may be good or bad, but it's a valid procedure. And so the question is that a good procedure? And I'm not going to get into it too much, but basically the punchline is that this isn't horrible if the number of classes, let's call that maybe k, is small. Oh, not that many L's in small. If the number of classes is small, this is actually okay, and can give you a reasonable classifier. Indeed, if I have a binary classification problem where k is equal to 2, and there may be some other little caveats. So let's say with some caveats. I'm not going to go into too much detail. Nothing too major, but there are some other little things that have to be true. But generally, the idea is that if I actually do this with binary classification, this will give me LDA. So with some caveats, but basically, this is going to give me back LDA in the binary classification setting. And that's something that can be shown analytically. That's pretty much exactly true. The problem is, as the number of classes starts to grow, this starts to get worse and worse. And LDA, something like LDA, will not suffer the problems that this will have. When k is large, we have what are called masking problems. And so let me just illustrate here, and then we'll call it a day. Here's what a masking problem is. Let's illustrate what could happen if I have 3 classes. So I have those, switching my colors here, but let's say something like this. And let's say something like my red squares over here. Now this may not actually produce, this exact data set may not actually produce a real masking problem. We'll look at it a little bit in the lab, and I'll give you a numeric example when it actually does cause a masking problem. And I'm going to plot here my discriminant functions for each of these. And it's possible, and what will happen if you do this regression approach with a bunch of classes is you're going to mask some classes. That some classes are never going to get predicted in a very kind of unfair way. So what could happen is I could learn my discriminant functions, and maybe my red discriminant function presumably looks something like that, right? So it's high when I'm near the reds over here, high over here, so I'm likely to predict the reds. It's possible, though, that my blue discriminant function looks like this, so high where we're at the blues. But what could happen is that I could get into a situation where maybe not the exact same slope, but my green discriminant function, this is probably not going to happen in this case. Let's move my greens real quick so it's a little more believable. If my greens are maybe a little bit more on top of my blue ones, you could end up in a situation where you might not get the exact same slope, but you could get something like that. And these could be maybe not exactly parallel lines, but they might be close to being parallel. And in this case, over here, I'm going to predict red squares because my red discriminant function is highest. So this is delta square. And over here, delta circle is highest. So I'm going to predict circle. But my delta x over here is basically, at least for the region we care about, is never the largest. And I never predict the x class by blue x's. Now this is a situation that will become more and more prevalent if I use that kind of linear regression approach and I build that linear classifier in kind of a silly way. This won't happen for LDA, and maybe next time we can talk a little bit about why this won't happen. It has to do with the fact that normal distribution, the tails decay exponentially. And so you're going to have kind of exponential decay as you move away from the means. And so you're not going to mask each other very easily because your things are kind of exponentially decaying. And so it's hard to mask one class with another. And so it matters. So you may say, well, LDA is just a linear classifier. But it matters exactly how you estimate these betas because you can get different answers. And if you do it in a poor way like this, you could get masking problems where it's going to give you a bad classifier because it's basically not going to be predicting one of the classes where it should be some region in here where we're predicting these circles. Okay, I'm going to stop there. That's our kind of grand tour on LDA, QDA, and a little bit of regression. And next time we'll talk about one more linear classifier and try to bring all this classification together a little bit. And then we'll be done with classification for a little bit.